All right, we'll give it a couple more minutes here. We're going to get started. For those of you that are joining us, we're doing a bulk power systems learning module, partnering up with PNNL, and we're going to cover topics on resource adequacy and other planning approaches. So give it just a few more minutes here. All right, well, welcome everyone, and good morning or good afternoon, depending on where you are today. I am a Principal Regulatory Policy Specialist with NARUC's Center for Partnerships and Innovation. This training is made possible with funding from the U.S. Department of Energy's Grid Deployment Office, and this is a collaboration between NARUC and the Pacific Northwest National Laboratory for today's training, and then we're going to do another one on Thursday, and then we're essentially covering a wide array of resource adequacy topics. And next week, similarly, we've partnered with Lawrence Berkeley National Labs with a training course that's going to cover generator interconnection processes and developments on that topic throughout the country. This is the third series of courses that NARUC is offering. We had another one earlier this year where we worked with ESIG, the Energy Systems Integration Group, on a variety of other topics related to the bulk power system. Those included the integration of utility scale solar, electrification and load forecasting, and energy adequacy and capacity accreditation. All those courses are posted on the website that you're seeing on the slide here. And so if you missed them, you can go take a look. We've got the recordings and the decks online for you to download. And if you really want to get into the foundational stuff, you can check out our spring 2021 training. And that was more sort of foundational impacts of DERs on the bulk power system stability, system balancing, things like that. Just a reminder, these trainings are designed to support you all, NARUC members. Specifically, we want to ensure this kind of information and these tools are useful as you all navigate the ongoing transition of our evolving electricity system in your respective states. And so, again, I want to make sure that this is useful. If you have any feedback or suggestions or would like to learn a little more about what NARUC is doing in this space, don't hesitate to reach out. My email is at the bottom of the slide there. I'd also like to highlight that we recently put out a resource adequacy report. If you haven't had a chance, take a look at that. It's on the CPI website. And we basically looked at different resource adequacy and planning processes throughout the country, and also covered recent reforms and enhancements that are being explored. And so finally, I just want to note that, again, these presentations are being recorded. They will be posted for download. If you have colleagues that couldn't make it today, we encourage you all to notify them of this and make sure they're aware of the this as a resource. So for today, just regarding our agenda and logistics, we're delighted to hear from 4 distinguished presenters. Juliet Homer with PNNL and I will be introducing each of them before they begin. And after each presentation, we're going to have time for Q&A. If you see some minor things that you don't understand or need some clarification on certain topics, just use that Q&A feature there, and the presenters can address them throughout their presentations. And then the more comprehensive, technical questions we can get into after they're finished. First off, we're going to hear from Dr. Marcelo Elizondo with PNNL. He's going to kind of set the stage here, kind of refresh us on the resource adequacy basics. Then we'll hear from Dr. Todd Levin with Argonne National Labs. Dr. Levin will discuss considerations for baseload retirements and more generally how assessing resource adequacy impacts can change with this evolving system. At 2:10, we're going to take a short break, and then we'll come back for the second part of today's course. BeiLi will talk about what's going on in MISO with their evolving planning practices and planning studies. And then we're going to move over and take a look at the Western interconnection. We're glad to hear from Nick Pappas with NP Energy. They recently, I guess he was involved in putting out a really useful report on the Western Resource Adequacy Program, or the RAP, If you haven't had a chance, I'd encourage you all to take a look at it. It was posted by GridLab, and there's a lot of really good explanation and background on that effort in the West. I think most instructors, hopefully you all can stick around. We'll have additional time for kind of some discussion and a group Q&A with all of you. But before I hand it over to Dr. Elizondo, I'd like to just thank Juliet Homer, who's been instrumental in pulling this all together. We hope to do more of these maybe next year. If you have any suggestions for topics, again, send them my way. We're open to anything and everything under the sun, as long as it relates to bulk power system issues. So I'm going to stop there. Juliet, do you have anything else to add?
No, thank you. I think I'll go ahead and just introduce Marcelo and maybe go from there.
Great.
Okay, excellent. So thank you very much, Elliot, and it's been a pleasure to organize this with you. Happy to be here. And Marcelo, if you want to go ahead and pull up your slides, I'll go ahead with the introduction. So Marcelo Elizondo is a principal power system research engineer at Pacific Northwest National Laboratory, or PNNL. He specializes in bulk electric system planning, resilience, and system dynamics. Dr. Elizondo leads projects for the U.S. Department of Energy and the U.S. Department of State on power systems modeling for resilience, clean grid transformation, high voltage direct current transmission, and cross-border transmission planning. He's helped develop reliability and resilience planning tools for bulk power systems and microgrids. Dr. Elizondo holds an engineering and PhD degree in power systems from Universidad Nacional de San Juan, with additional academic experience at Carnegie Mellon University and Supélec in France. Thanks for being here, Marcelo. Take it away.
Yeah, thank you, Juliet. Can you hear me okay, no?
Yes, okay. Sounds great.
Okay, perfect. Thank you very much. It's very good. It's a pleasure to be presenting here, and please, I think we're gonna have a presentation for 20 minutes and then have questions. So and then so please, yeah, let me know, or you can put questions in the chat. Okay, then yeah. So as Elliot and Juliet mentioned, I'm going to present some fundamental concepts about resource planning with some considerations on capacity expansion, balancing reserves, and adequacy. And I'm going to talk about the evolution, how planning has evolved as more renewables have been integrated over the last years in power systems around the world. And especially now, this is very of high interest, is to continue to evolve power system planning methods and tools so that we can achieve the objectives of decarbonizations or the renewable portfolio standards that many of the states have in the US, for example. Yes, so then, but I'm going to cover some general aspects, and I'm going, and a couple of aspects I'm going to expand a little more, but feel free to we can make this a conversation, and towards the end, you can ask about any part of the process that I'm going to discuss. Yeah, so let me go to the next slide. Yes, so why planning for renewables? So especially you can see in this figure of this is the renewable share of the annual power capacity expansion globally. This is a figure from IRENA. The reference is at the bottom, and you can see how renewables are growing around the world, and also that includes, of course, the US. Then and you can see how and this is a trend that has been going on for a while, and now to achieve the objectives of decarbonizations, like those of the federal government, for example, this trend needs to continue and perhaps being accelerated. So these technologies, especially wind and solar generation, are key for decarbonization. There is all and so then it is expected that we need to plan and prepare for integrating these resources in the power grid. But of course, these resources have challenges for integration. So their output of particularly of wind and solar generation is variable, and it is also uncertain. You need forecasts for which there has been a lot of progress in forecasting for the next days or next few hours. But still, if you want to forecast for the next week or for the next month, this is more challenging currently. So then it is very important for the power system planning tools and methods to account for the variability and the uncertainty on the output of these main resources, which are key for decarbonization. So then we need to plan for flexibility to deal with this variability. So, and that flexibility can come from other generation resources, for example, hydro generation, natural gas, or retrofitting other plants. Energy storage is key, and especially if we are looking into decarbonizations, then we cannot use natural gas, perhaps, no, or so then. The resources that are traditional resources are more limited now, because you could use biodiesel or this type of fuels that are more similar to the resources that the utilities are used to using. But then there will be some more reliance on energy storage to cover for these needs for flexibility. Another thing that could be done is a controlled curtailment of solar and wind generation. And in addition to this, these are developing technologies. Their costs are decreasing, but also their standards for large-scale integration are just being developed. Especially, one example is the use of power electronics to interface wind and solar generation and energy storage is very different from what the power system has been used to for the last 100 years, which is the synchronous machines. So then, and I think there will be one presentation coming up covering these topics of stability and the energy conversion and how to integrate from that aspect. But that's one aspect of the standards that are evolving. Additionally, so the planning methods, we have seen that in the last 15 years or so, the planning methods have evolved to integrate the renewables, and they continue to evolve now. So then we are going to focus, review the planning processes and some fundamental concepts of those. So here we have the planning studies for integrating variable renewable energy, and this is an illustration of a process that is kind of typical of what is being used now, but this in here you have how everything has sort of evolved over the last year. So basically, a key part is to understand the variable renewable energy resource data. So, for example, what in our period of study, if we are considering a future system for the next 5 years, for example, we need to create the scenarios of the solar irradiation and the wind speed, so that can give us an idea of how the generation is going to evolve. Based on that, and where in which places the resource is better, and this type of things. So with that information, that is fed into capacity expansion, which the decision there is to decide where to build generation and where to build transmission as well. And that could be, at the national level or at the regional level. Usually, these type of models, given the complexity and the level of decision that these models are trying to cover, they usually there is a need to simplify the physics of the model. So, for example, the transmission system is considered in a simplified way. But because it's usually those lead to an optimization, very large optimization problem. So then you have to simplify some things. So another type of study that could be usually done in a sequence after you have solved for capacity expansion, you can do adequacy. So, and the adequacy look for answering the questions that are there enough resources in the system? Is there enough transmission in the system? Enough to supply the load, that's needed. And this type of study can get, especially with variable renewable energy, so as the generation changes over time, the availability of generation changes over time. So then it creates the need to assess the adequacy also in a very detailed way in an hour-by-hour basis. Other parts is that is very important also for planning for balancing reserves. So as the system is changing, so it is important to consider if there will be enough resources, enough flexibility in the resources to provide balancing services in the system, and how much of reserves that are flexible and are needed in the system as it evolves. Another type of study is also called a production cost model, that this is a simulation of the operation of the system. It could have resolution of 1 hour or resolutions of 15 minutes, for example. But it looks at simulating, for example, a full year of operation and how the generators are being dispatched, how much, and of course, in all of this process, you need the data from the variable renewable energy resources. And this is usually you need the data in a chronological way with high resolution as well. So so in this simulation of the operations, you try to identify operational challenges. But again, as we are going down these different type of studies, also the complexity of the models are progressing. When we are here at the bottom of the production cost model, what's happening usually here, you consider the network. You can consider the transmission network in detail at the substation level, which is called a nodal model. And then that type of, but however, you still need some simplifications to be able to simulate the operation of the system. And those simplifications usually ignore the voltage control and the reactive power control of the system and only focuses on the active part of the system. So then there are some reliability aspects that cannot be captured in this type of simulation. So then to add those details and be able to assess the feasibility in more detail of this system, and then to assess the reliability also with some more details. It is what is called power flow and stability studies. And then here you consider, voltage stability, frequency stability. Here you can do detailed contingency analysis on this type of models. So this is, a quick pictures on all of the different type of studies that are usually used today, and this is as the planning processes have evolved. At the bottom of this figure, you can see the resolutions of each type of models. Like, for example, capacity expansion will have resolutions of typically of years, and the horizon can be 10, 15 years. and as you go down this in model detail, then you can have a higher resolutions of this time, or yeah, so the resolution will be hours to minutes for this adequacy, balancing and production cost model. But then for power flow is and stability studies, it could be seconds to sub-seconds. Yeah. Then now I'm going to show you some examples on when this type of framework has been applied in some studies recently. First,
Dr. Elizondo, sorry to interrupt. We just had a quick question in the chat here. On the prior slide,
yeah,
there's a question: when is resilience looked at on
yeah.
this timeline? I don't know if you can speak briefly to that.
Yeah, certainly. That's an excellent question. Yeah, the resilience can be looked at in several of these aspects. Because, for example, resilience, you can think about extreme weather related resilience, for example. And you can look at that in the adequacy step, for example, or in the production cost model step. For example, depending on the duration of the event, you can have, for example, something like a heat wave that could be several days of extreme weather, and that could be affecting the operation of the system. So one example could be that you can, when you're doing your simulation of hourly operation of the system, maybe you can create a case where you have this heat wave with the load has increased, the generation is challenged. For example, the gas generation is derated because of the high heat. As is happening in the Pacific Northwest, sometimes when the heat wave there is also the wind generation of wind is sort of stops. So then all of those effects you could consider in this production cost model part. Other things that could happen is, for example, here in the Northwest, is that the snow pack gets melted quicker, which affects the hydro generation and affects the production of the hydro generation. And again, at this time scale, you can do this type of analysis. There are some of my colleagues here at the PNNL have done some of those analyses. Another thing that you can use at this step, power flow and stability, you can also simulate resilience events. Like, for example, you can have what we do, for example, for Puerto Rico, we simulate hurricanes, and we can see contingencies of power lines going out of service because of the high winds, for example. For example, things like wildfires or contingency analysis can be done given that you have a very stress condition. Then on top of that, you can do contingency analysis, for example. So yeah, so it can be part of this process, the resilience. But yeah, like traditionally, all of these have been covering the day-to-day reliability usually. But now you see many examples of resilience being considered in these steps as well. Yeah, but that's a great question, which I think in this presentation I don't cover resilience enough. But but that's why I appreciate the question. That's very good. Yes, so some example where this process have been applied is, for example, in the offshore wind integration study for the West Coast, where there is a colleague from mine here at PNNL recently ended this study, where offshore wind generation has been studied here in the Oregon coast and also in Northern California. And they have studied ways of integrating this and building transmission in the offshore to be able to integrate this generation. And the process is very similar to the previous one. No? So we have a characterization of the variable renewable energy. This is combined with the rest of the system data sets. Then you have a step of production cost model, power flow analysis, and then some contingency and stability analysis. And this is, as you see, this is iterative. You go back to the process and rerun. And in this case, you can see, as I was relating to the question, they inserted some resilience events in the production cost model step. So that related to the question that was asked in the chat. No? But this illustrates how the structure is very similar. Other example is the Puerto Rico 100 renewable energy study. This is currently going on. It's about to finish, but in this case, there are, in addition to the stakeholder engagement and scenario generation, then you have in this step, in between the scenario generation and capacity evaluation, you have capacity expansion, production costs, and resource adequacy on this side. And later in impact analysis, you have a power flow and bulk system analysis and reliability. And in this case, the resilience appears in the power flow and type of the analysis, no, which is a different event like a hurricane appears in here, no. Then another example is the National Transmission Planning Study, where you can see similar type of structure as well. So you have steps of capacity expansion, resource adequacy, and then followed by production cost modeling, which is you study the grid in more detail, and also interactions with power flow contingency analysis, and also AC power flow contingency analysis as well. And in this case of the national transmission planning, this study is looking for is determine the high value transmission expansions to reach the objectives of full decarbonization of the electricity grid by 2035. No, yeah. So then, yeah, and you can see, it's again similar sort of sequence of processes of these models, modeling activities. No. But then, what is the capacity expansion? So in the capacity expansion, what we look for is to decide when to build, and perhaps I should I should go a little faster. So then, but the important part is usually transmission expansion is done in a generation expansion is done, and then transmission expansion is done separately. There are some proposals where they try to integrate these two steps together, but in practice, usually this is more common. So there is a generation expansion plan that is done first, and then transmission expansion is done after the generation expansion is known. But usually the time horizons are for 10 to 50 years. There is also, I have here a slide of typical or some examples of tools, commercial tools and free tools for capacity expansion. Then in the case of resource adequacy, we mentioned that this is to evaluate if there is enough generation and transmission to supply electricity. In the case of the resource adequacy, what has been done traditionally is consider the availability of generation and transmission, and considering the probability of failure of the resources. So, and trying to answer the question if I have enough resources in the system, irrespective of the cost of the resources. I want to know, do I have enough, and when, how much when I'm going to face challenges, and how large is the shortage that I'm expected to have of energy. No, that was traditionally, like, in the 1950s or 60s. There were several methods that were developed, but those were for the traditional power system where you have a full controllability of your plants. So basically, that was focused more on the failure probability of the machines and the transmission. But now with the renewables, there are more need to include chronological hourly operation. There is also interest on including weather data sets for several years in this type of analysis, because the weather will influence the load and also the generation. And usually the horizons for this type of analysis could be seasonal. I want to know if in next season I'm going to have enough resources, or if next year I'm going to have enough resources, or it could be part of a long-term planning study. As I mentioned before, here you could also include extreme weather events. I put also some very good presentations here at the bottom as a reference to learn more about the topic. Let me see if I can accelerate a little bit. So the other part is the flexibility. So we can measure the flexibility, for example, in capacity requirements, ramp rate, ramp duration, and this type of, which is, when you have variability in the system from renewables and load, for example, you need your flexibility to cover capacity, ramp rate that speak to how flexible and how fast these resources should be, and also the energy that you need. So to evaluate the flexibility, especially for the planning, so that you can plan to have enough flexible resources in the system, we have a process and tool at PNNL that is called Graph Plan, that this one evaluates the reserve requirements, and also evaluate if there is enough flexibility in the system. So focus on these two questions: what are the requirements, and then my flexible resources are enough to cover for the reserves that are needed. So, and this is based on forecast and operational models. Those are based also on the characteristics of the systems. It depends on how the operators, what are the practices, the operational practices, their dispatch, the schedules, their definitions of reserves, their forecasting processes, and also how those forecasting processes could evolve in the future. And we have applied this in several places, particularly in the Western interconnection. This has been applied a lot. In the reference at the bottom, you can see some of the examples of the application on the Western interconnection. And then this part of this methodology has been also integrated with a Hitachi Grid View software, which is a production cost model, and where you can include this type of evaluations of reserves. Another part is the conversion between the type of models is very challenging. So when you do the simulation of the operation, and then if you want to do a more detailed reliability study, it's very challenging to convert in between models. So there is something called the chronological AC power flow automated generation tool that can automatically convert simulation results of simulations of the operation into a more detailed model, so that you can study the reliability. And this is important because typically it takes several days or months to create to make a conversion of a single snapshot to depending on the experience of the modeler. But then this tool uses some some automation and some machine learning techniques to help the conversion of these models, and it is very successful. So you can do hundreds of snapshots of representing different hours of operation in a matter of seconds, and so it's a very good tool. Yes. So finally, just to conclude, there are some key aspects of planning. So that we discovered, that I talked about, is the generation and transmission expansion. We review concepts of resource adequacy, production cost, and balancing reserve planning. And also some conversion into power flow to enable stability and more detailed contingency analysis. It is also important that these type of models can capture multi-year weather data and also the effects of extreme weather events. And the power, and we also have seen how the modeling and planning processes have evolved significantly over the last 15 years. And I believe that still these methods need to continue to evolve so that we can plan and prepare for a decarbonized grid in the future. So yeah, so with that, I think I might have, not sure if we have some time for questions. So, yeah.
Yeah, thanks, Marcelo. Excellent. Elliot, do you want to lead the Q&A?
Yeah, sure. We had a question earlier. I didn't want to interrupt you again, but there was a question in the chat. Shouldn't we look at the resilience in the power flow analysis or the EMT analysis before the production cost modeling is done? Do you have a response to that?
Okay. Yeah, no, that's interesting. Well, usually, I think it depends on how we are doing what type of study we are doing. Is it a study of the operation or is planning for operation of a system that we have now or in the future? For example, in the future, you can have a significant amount of new generation in the system. So first, you might want to know how which generators are going to be online. Once you know which generators are online, then you can say, okay, I will take this particular hour and I will run a power flow stability analysis or electromagnetic transient type of stability analysis, but those focus on this instant. If in this instance I have a contingency, then the power flow, stability, and electromagnetic transient models can tell me what's going to happen. But the production cost model can make a simulation of a full year. So usually what's done in a long-term planning simulations, you simulate the full year, then you can select what is my which hour am I interested in modeling, which traditionally, utilities will choose the summer peak, winter peak, a couple of snapshots to do those analyses. But now, if the system is changing a lot, if you are including a lot of new generation, then first you need to know which is my more challenging hours. When should I be, which hours should I be selecting for this? So that's why, usually the production cost modeling is done first, and then the stability. Yeah.
Great. Thanks so much. That was a terrific and in-depth presentation. I had another question about interregional impacts and balancing, but given our time, we might save that one for the group discussion at the end here. And so with that, again, I'll thank you again, and we'll move along here to our next presenter.
Thank you.
Okay, can you hear me all right?
Yeah,
Yeah.
I'll give you a quick intro if you don't
Sure.
mind.
Let me get it. Yeah, I'll get the
sure.
slides pulled up while you do
Okay,
that. Yeah,
great.
great. Thanks.
While you're doing that, Dr. Todd Levin is the electricity markets team lead in the Center for Energy, Environmental, and Economic Systems Analysis at Argonne National Laboratory. His research interests focus on utilizing advanced optimization and simulation methodologies to model complex interactions in electricity markets and to quantify the implications of domestic energy policies and regulations. Dr. Levin holds a BA in physics from Northwestern and a PhD in industrial engineering from the Georgia Institute of Technology. So, Dr. Levin, take it away.
There we go. Someone muted me. All right. Hi, everybody. Thanks for tuning in. So I think what I'm about to present will complement Marcelo's presentation nicely. He provided a nice kind of high-level overview of some different concepts. I'm going to dig a little bit more into some numerical examples of resource adequacy. Just again, touching on, I guess, that definition or that concept a little bit more narrowly and dig into some of the metrics that are currently used or have historically been used, and also those that are emerging. So with that, I guess I'll get into things. What is one second, there we go. So what is resource adequacy? I mean, I think this was kind of covered, but just to drive home the definitions, resource adequacy reflects the ability of a system to serve electricity demand at all times. So from a high level, it's exactly what it says. The definition says there are adequate resources in the system. It is not synonymous with reliability. It's really one component of reliability. And so we just had a question about resilience, which I think was timely. There's also issues of operational reliability, which has more to do with how those the resources in your system are operated in practice. But resource adequacy is more of a little bit more of like an investment scale metric, and it's kind of assessing from a big picture: do you have enough generation capacity primarily in your system? And that definition is evolving. Traditionally, it's been built really around just thermal systems built around thermal resources. You look at installed capacity, you adjust a little bit for expected outages, and that's your gives you a picture of resource adequacy. Now, with renewables, weather-dependent renewables coming to the system, battery storage, maybe more transmission constraints, it's becoming a little bit more complicated. And so that's what I'm going to talk about a little bit more. There we go. Okay, so just to establish a few definitions. So traditional metrics that you may be familiar with already, but installed capacity is essentially the maximum output of a generation resource, usually in megawatts. Unforced capacity is essentially that installed capacity derated or reduced a little bit based on what can reliably be accounted upon to serve peak demand. At least that's the traditional approach. So for thermal fossil type plants that are dispatchable, it's generally similar to installed capacity, anywhere from almost 100% to maybe 85%. And that's again just derated based on some outage probabilities. For wind and solar, it's a lot less straightforward to determine. So you can look at the expected output of wind and solar in that one peak hour of the year, but that's not going to be necessarily the same every year because weather conditions change. Your kind of most needy periods of the year may no longer be the peak load hour, but actually the peak net load hour, which depend on how much wind and solar is in the system and also depend on weather conditions. And so it gets complicated. So traditionally, there's a conversion factor from ICAP to UCAP that's called a capacity credit. Some regions have fixed capacity credit values for wind and solar. There's different methods that are used to calculate those in different systems, and there's no single straightforward method. Another approach is to kind of start looking at newer resource adequacy metrics that aren't just based on UCAP anymore, which is what we'll talk about. But again, the most predominant traditional resource adequacy metric is called the planning reserve margin, which again you may be familiar with. And put simply, this is essentially the amount by which UCAP exceeds the forecasted peak demand hour in the system. So if you have a peak demand of 1,000 megawatts and you have 1,200 megawatts of installed or of unforced capacity, you would have a 20% planning reserve margin. And again, traditionally, these systems are planned based on a fixed planning reserve margin, somewhere in that 15-ish% range, depending on your system. And that's worked well as a proxy metric for reliability. This is resource adequacy, but it's worked well as a planning metric in thermal dominated systems, but is becoming less appropriate in emerging power systems. Okay, so I want to give an example. I told you there'd be numbers here, so it's kind of, I think this helps to drive home kind of conceptually what a planning reserve margin is and why it is or maybe isn't a suitable metric for different systems. So this is an entirely hypothetical system with 500 megawatts installed capacity each of a handful of different technologies, nuclear, coal, gas, wind, and solar. And it translates to a, let's say, I'll just pop all these up here. These are the unforced, the UCAPs based on these capacity credits, which are, again, not unreasonable based on some definitions, but also just purely hypothetical for this example. And so we're taking a system with 2,500 megawatts of installed capacity, peak demand hour of 1,600 megawatts. You do the math, translate ICAP to UCAP, you get 1,850 megawatts of UCAP, do your division, and you get a planning reserve margin of just over 15%. So again, a contrived scenario to get you to around that 15% mark. Okay, so that's like traditionally a reasonably planned, reasonable planning reserve margin, a reasonably, quote, reliable system from a resource adequacy perspective, without doing that detailed reliability assessment. Okay, so what happens if we shift this generation portfolio a bit? We're looking at emerging, kind of modernizing power systems. We retire all of the coal in the system, replace it with, replace 500 megawatts of coal with 600 megawatts of solar. Do the math, solar replacement to get an equivalent UCAP value, take the ratio of the two capacity credits. You do all the math, you have a system with the exact same planning reserve margin, but clearly this is a different system. The reliability of this system may or may not be different, but it probably has different considerations just based on the reduction in dispatchable coal capacity and the increase in non-dispatchable solar capacity. Yet the reserve adequacy metric, planning reserve margin, is the same. Okay, taking an even more extreme example, retiring all the coal, replacing it with wind. Wind has a much lower capacity credit in the traditional sense, because solar generation is highly correlated with peak demand hours in the middle of the day. When it's hot, there's lots of sun, air conditioning loads are high, solar generation is high. Wind is generally a little bit more available in the evenings and overnight when demand is lower, so it has a higher capacity factor, meaning it generates more energy, but that energy is not as well correlated with peak demand conditions, and so it has a somewhat lower capacity credit. So you do this math, take a 20% capacity credit, take the ratio, and you need a lot more wind to get that same amount of UCAP, and you have a third system with the exact same planning reserve margin, but again, it looks very different and will have different reliability considerations. Okay, so that is, again, hypothetical, kind of contrived example, but just to drive home kind of how to interpret a planning reserve margin when you see it, and understanding that that's not the only metric that is going to matter in assessing the resource adequacy of your system. So shortcomings of the PRM, it really only accounts for the single peak load hour. Peak net load, which is demand minus wind and solar generation, will shift as the system evolves. It may even shift year to year with the same portfolio just due to weather conditions. And the capacity credits of wind and solar depend on the whole system portfolio. So I'm going to now demonstrate another numerical example, taking different systems with the same planning reserve margin and looking at this kind of stylized reliability assessment. I'm going to have a slide here in a second with a lot of disclaimers so people don't, so you don't interpret too much into the specific numerical results, but just I think the numbers help to kind of drive home the concept. So what I'm going to do is, this is a simple merit order dispatch. So that just means that you dispatch your capacity in this order. So you'd kind of choose to dispatch all of your solar, then all of your wind, then all of your nuclear, then coal, then gas. And that's roughly in order of the marginal cost, or the variable cost of generation. There's no consideration given to startup costs or minimum generation requirements or anything like that would be included in a more detailed production cost model or reliability assessment. And what we're going to do is add progressively more solar to the system and kind of show how that impacts the interplay between planning reserve margin and some reliability metrics. Some emerging, I guess I should call them emerging resource adequacy metrics is what they really are. And this is based on some basic data taken from NREL's Reed's model. And this is analysis that was done for regulators in New Mexico initially. So it's loosely based on New Mexico, but it's not again, detailed New Mexico specific analysis. Okay. So here we have a simple merit order dispatch, hourly dispatch of this system. June 29th, this is the peak load hour of the year. You can see peak demand is 4 p.m. Here, and here's when you dispatch your system like this. Here's how things stack up. You see kind of the nuclear providing your base load. Again, and once more, I want to mention this wind and solar resource availability data and the load shape are taken from New Mexico. This generation portfolio is entirely contrived. It is not the portfolio in New Mexico or any particular state. So what you see is some unrealistic effects. The coal generation is ramping a fair amount to kind of follow the net load. But all in all, you get a perhaps semi-realistic dispatch portfolio with the some gas coming in the shoulder and solar providing peaking in line with net load peak load conditions. Okay, so what happens if we switch and displace 100 megawatts of coal to provide to solar? It'd be 120 megawatts of solar capacity. So what you get is, you can see this kind of shift in generation. There's more solar generation. Nothing really changes. You still have enough capacity to serve demand during your peak hour. Okay, let's take it one step further. Now we're going to remove 200 megawatts of coal and add 240 megawatts of solar. Again, based on the slides we saw earlier, this results in the same planning reserve margin for the system. So that reliability metric is the same, or resource adequacy metric is the same, sorry. But now what we're seeing is, because we're displacing coal with solar capacity, where generation is not available at 8 p.m., you actually start to see a period where all load cannot be served at 8 p.m. And notably, it is not during the peak demand hour. It's actually during the peak net load or net demand hour here, which is your total demand minus solar generation minus wind generation. So this is now your new peak net load hour, and you're starting to see this, lost load or unserved load creep in again in the stylized system. Keep stepping through that. You see, adding more solar with that same ratio, and you start to see more and more reliability issues arise in that shoulder. Potential reliability issues arise in that shoulder period where solar generation decreases. All right, so to the more extreme again, we just showed that this portfolio replacing 500 megawatts of coal with 600 megawatts of solar has the same same resource adequacy, planning reserve margin, but different outcomes in terms of expected unserved energy. Okay, so the shortcomings of the PRM. This is another way to demonstrate kind of what I showed before. All these examples have the same PRM, but they do not have the same level of reliability. And this required coal to solar replacement ratio really changes as you add more and more solar to the system. And in fact, no amount of solar can be added to avoid these outages at 8 p.m. because if you look closely, there's no, or maybe maybe it's a tiny sliver. I think it's actually zero resource potential for solar in that hour. And so no matter how much solar you add to the system, you're not going to be able to resolve that outage without storage or some other resources, for example. And so this clearly demonstrates the importance of energy storage in systems with increasing solar and wind penetrations, and also just considering a whole portfolio effect. Okay, so I'm going to step through one more quick numerical example demonstrating some emerging resource adequacy metrics. So trying to be precise with my language here. So planning reserve margin is a traditional resource adequacy metric. Some new metrics are loss of load expectation, the loss of load probability, and expected unserved energy. So these are kind of the expected number of let's see, days where you will experience an outage, the probability of demand exceeding generating capacity during a time period, and then EUE is, I think, kind of a little bit more commonly used now. It's a little bit harder to assess because you actually have to do some simulation, but it's the amount of unserved energy, not just the probability of an event occurring, but it also factors in the kind of magnitude of that event. So the total number of megawatt hours or gigawatt hours that you might expect to have energy shortfall. Okay, so with those metrics, there's another new metric that's kind of emerging to replace planning reserve margin, and really the capacity credit that translates ICAP to UCAP is effective load carrying capacity. There's a kind of two different approaches to calculating ELCC, and you can use any of these metrics to to assist in that calculation. Let's focus on the I guess my calculation actually uses this generation approach, but I think the load approach is a little bit more clear to understand. So it's saying the amount of additional load that you can add to a system along with a resource while maintaining the same reliability level, the same loss of load expectation or expected unserved energy, whichever metric you choose. So add one megawatt of solar generation. How much more load can your system support? Is it 1 megawatt? Is it half a megawatt? Is it, a tenth of a megawatt? And that ratio will get you the ELCC. It's a more precise metric, but it's also more complex to determine. You can't just kind of use a spreadsheet to do your calculation. You actually have to run some production cost and simulation type models to do this assessment. Okay, so here's all of my disclaimers. Again, this is really just demonstrating the method. Very stylized. This true calculation would require sophisticated tools. I'm going to use this merit order dispatch tool again just to demonstrate the effect. Okay. So here is the merit order dispatch for an entire year, just to kind of show what that looks like. You see these like coal and nuclear cycling effects that aren't necessarily realistic, but you can see the kind of the general idea of wind and solar alignment and daily peaks and things like that. So we're going to quickly walk through this this approach where we're basically going to reduce coal by 400 from 500 to 400 by 100 megawatts and see how much solar capacity we need to provide the same reliability level. So this is actually the generation-based approach to calculating the ELCC. So what we have here is, I'm not showing how this is all calculated. This is just in a simple spreadsheet model, but we have a system here with this generation mix. The merit order dispatch results in 3 hours with lost load and a total of 29 megawatt hours of lost load with this assessment. That's roughly in line with this very historic and kind of falling out of favor metric, the 1 day in 10 reliability assessment metric, which sort of says, assumes appropriate outage of roughly 1 day every 10 years or 2.4 hours a year. So here we're hitting 3 as a target. Removing 100 megawatts of coal capacity, you can see it increases your lost load, hours with lost load, and your total lost load significantly. And then what I do is I just kind of iteratively add solar capacity until you get that same number of hours with lost load, noting that the actual expected quantity of lost load in megawatt hours is a little bit different. You take the ratio of these two, the subtracted 100 megawatts, added 124, and you get the ELCCE of solar. So 81%. If you recall, in my initial example, I had assumed a 75% capacity credit for solar. One other key assumption is that this assessment should really be done based on a what's called a perfect resource, which means a resource that is, 100% dispatchable, no ramping constraints, no PMIN constraints. I'm using coal as a stand-in for that because in the merit order dispatch model, it actually is that. In reality, that's not the case. So one more disclaimer, but again, proof of concept here. Okay, so I'm going to kind of quickly step through the process of reducing this, taking more and more coal out of your system and replacing it with solar. Here we're dropping 50 more megawatts of coal, seeing how much new solar we need. Well, this ratio is actually increasing. The amount of solar you need is increasing. And so you're getting a smaller ELCC. The incremental credit effective load carrying capacity of that new solar capacity is now only 56%. We take it one step further, add an additional, retire an additional 25 megawatts of coal. Now you need a fair amount more. You need another 221 megawatts of solar. You're only getting 11% credit. And then finally, this effect that we're seeing when you drop from 325 to 300 megawatts of coal, there is zero solar generation potential in this hour at 8 p.m. So it doesn't matter. You can add, 2,000 megawatts of new solar capacity. You're never going to serve that lost load in that hour. And so effectively, the ELCC of solar is zero in this contrived scenario. So what are the implications here? Again, I know that's kind of quick. I'm hoping that the numerical example helps kind of drive things home conceptually. I do want to state one more time that the actual calculations are complicated, and that's part of the challenge, is that you need complex power system modeling tools. It's harder for, say, regulators to assess the calculations that are done by utilities because they're going to be based on executing these complicated tools, and we'll need to have more insights into how those numbers are calculated. But the core is that you should expect that the marginal resource adequacy contribution of wind and solar will diminish as more wind and solar capacity are added to the system. And that's because their collective availability is correlated. You might have some statewide diversity, region-wide diversity, but generally generation will be higher in the afternoon and essentially zero overnight. You need models to assess the true resource adequacy implications. And another key, I didn't touch on storage at all here, other than I hope these examples demonstrated why storage is important, but it can help to mitigate these effects, but also adds one more layer of complexity in calculating reliability, resource adequacy contributions, of individual resources or as like a combined, say, solar storage hybrid facility. So considerations specifically for regulators, I kind of touched on this. PRM is traditionally very easy to calculate, but kind of imperfect. No single metric is a substitute for a full reliability assessment. Resource adequacy metrics really are intended to give you a easier high-level snapshot of future adequacy, but you also would want to see a more detailed reliability assessment or resilience analysis, as was mentioned earlier. Regulators can use these metrics to assess reliability impacts of fossil retirements, but it's important to understand the value and limitations of the different metrics being used. Regulators will often rely on others to calculate these metrics and then be responsible for validating them. And so, that may become increasingly challenging as more sophisticated models are used, that you might not have, immediately have full insight to all the assumptions and the detailed analysis that's conducted. I'll just close here. Here are a couple resources. There's a lot more out there, but these were ones I found that kind of give a nice high-level overview of some of these metrics. But it's a pretty active area of research these days at labs and academia, industry, and so there's a lot of emerging work on kind of understanding how wind, solar storage, kind of new dispatchable, hydrogen or CCUS or other dispatchable renewable technologies might help to satisfy future resource adequacy requirements. Okay, I think I have a few minutes left for questions. I haven't been able to monitor the chat, but feel free to speak up, or Elliot, if you're able to moderate, that'd be great.
Yeah, sure, Todd. Thanks so much. That was really great. We had a question earlier. I didn't want to break your flow, but given the amount of thermal generator failures cited by the FERC-NERC Winter Storm Elliott report. Is anyone revisiting the UCAP ratings for those types of facilities? 85 to 98% seems high compared to the observed performance during that event.
So absolutely. So that is a good point. So one, I think, really important factor that I mentioned is that those rates generally assume that thermal outages are not correlated, meaning that when you have an outage at a thermal plant, it's due to an unforeseen, mechanical maintenance issue, something like that. And it's not necessarily, there's not like a large scale correlation between gas outages throughout an entire state. Clearly, that is, not the case when you get fuel supply issues or weather issues that do lead to correlated outages. So absolutely, that can and should be revisited. That does kind of get a little bit more, there's this relationship between resilience and resource adequacy, and that might get a little bit more into that area of, like a resilience analysis or more of a reliability assessment. But you're completely correct that, you might want to revisit some of those assumptions. And yeah, I'll leave it there, but totally agree. Let's see, any other open questions? I'm trying to catch up here, the text.
I don't think in the chat, but
Okay.
I guess I'll throw one at you if you don't mind. You mentioned this sort of new multi-metric approach of looking at UCAP, looking at beyond the reserve margin. It seems like, and E6 talked about this, kind of the pillars of things to think about when you're assessing existing and future resources. How do you sort of walk that line between introducing new metrics that people are going to have to sort of understand better and dig into the weeds a little more, because some of these new things are a little more complex? And then are you going to, do you think the reserve margin is going to kind of go away, or do you think it'll still be there, but then you're just going to be layering additional sort of metrics on top of it?
Yeah. So there's a couple things there. I think ELCC, you'll probably see ELCC emerge as a more common metric. The challenge there is that it is extremely situationally dependent. So, I'll get people to say, okay, well, what is the ELCC value of solar? And that's not an appropriate question. It's what is the ELCC value of solar in, this region, in this future with like this generation portfolio? And that makes it hard because you kind of lose a little bit of that intuition for what the value should be. So I'm not sure what the best answer is in terms of balancing kind of the need for metrics like that with the fact that they are inherently a little bit more complex. Another kind of more drastic shift could be moving away from, and so Elliot, as you say, ELCC is kind of used to translate back to that traditional planning reserve margin, to kind of translate installed capacity to some form of reliable capacity, or firm capacity, or whatever you want to call it. Another concept is as we move towards more renewable dominated, weather driven, resource dominated systems, is getting away from a kind of a capacity planning target and to more of an energy planning target, what's called like an energy limited system, where you're really more concerned with your ability to kind of have enough energy like throughout the day and then move it through time with storage devices or things like that. And it may be the case that sort of a peak demand based or peak net load based planning target is not the most helpful planning target to be using in the future. But we're probably a little bit away from that, but that's something you might see discussed more in like 100% or 90% decarbonization type scenarios.
Great, really helpful. Yeah, I'd say, I think it's at the top of regulators' minds of how they can stay on top of these sort of evolving procedures on how we look at the system and plan ahead. So I think we can maybe take our break now. We try and break these things up so they're digestible. We can step aside for about 10 minutes and reconvene here at 2:20 Eastern, and we'll hear from our final two presenters for today. So thank you all. All right, everyone. I think we're gonna get back to it here. We've got 2 more presenters this afternoon, and first we're gonna hear from BeiLi with MISO. Ms. Lee manages the strategic assessment team at MISO, assessing the effects of emerging trends and drivers on the energy industry, as well as providing insights and solutions gleaned from the in-depth look at the challenges of the rapid energy system transformation. Ms. Lee has over 15 years of comprehensive experience in the energy sector, working in real-time operations, energy market design, economic planning, and corporate strategy. Ms. Lee has a Master's of Science in Electrical Engineering from Purdue and an MBA from the University of Chicago. Ms. Lee, can you hear, or is your mic working okay?
Yes, thank you, Ali.
Yeah.
Can you hear me
Great.
okay?
Yeah, coming through loud and clear. Are you okay to share your screen?
Absolutely. I do
Great.
have a little bit trouble sharing my video, so which is great. And so I will just get ready to share the presentation. So give me 1 second.
Looks good.
Perfect. Thank you. Just want to, first of all, give an appreciation to my colleagues, Zainiruk and also PNNL, as well as the Berkeley Lab for the invitation to share MISO's process. And also Dr. Elizondo and Todd gave a really good foundation on the principles of resource adequacy. And so what I'm going to pull back the conversation a little bit and just share with you on how do we use some of the information, how do we use the principle in looking at the resource adequacy construct for MISO. Right. And so for today's discussion, we'll go through some of our process and really just highlighting 4 key takeaways. Number 1 is how we can partner. So approaches that we're taking into to interact with states and members in the purpose of maintaining visibility across planning and operations timelines. This is to ensure resource adequacy and reliability for our system. And then second point is how you can leverage our work. We will introduce some frameworks and give you different kind of snapshots into our process. And so you can see how this can help you and also help our members with their utility planning. And moving forward, so you heard quite a bit from both previous presenters on our industry is changing. And so we'll also give you a lens through how we actually plan to change with the changing landscape. And finally, just very important thing for us to highlight on the importance of collaboration between RTOs, members, and states. So with that being said, again, just to summarize, I think Todd did a really good presentation on all the different parameters and metrics that we have in the industry and how the changing landscape is changing how we have in this resource adequacy conversations. And so we talked a lot about resource portfolio, but that's just one of the factors that changing, transforming our industry. We also see, again, a lot of conversations about flexibility. Do we have the fuels that we need for some of these thermal generations? And extreme weather has become tremendously prevalent and increasing in frequency. And so it's really forcing a significant portion of our fleets out of service. So how do we think about resource adequacy capturing these kind of impacts? And then the last element is electrification. It is still early in stages, but the momentum is picking up. And we have seen and we will continue seeing significant load increases at a pace that we're just not used to. So all this is summing up preparation for these increasing risks and changing conditions require an improved understanding of what we're currently doing in terms of resource adequacy construct, as well as identifying any kind of additional needs moving forward to ensure reliability and resource adequacy. The previous presenters already shared about resource adequacy. And so just to reiterate, this is just to ensure we have enough available energy to meet peak demand at all time. And this is a key function of MISO. And so our resource adequacy construct complements the jurisdiction that regulatory authorities have in determining the necessary level of adequacy. But it also works in concert with utilities that provide demand forecasts that help drive the development of local and as well as regional requirements. And so MISO serves as an intermediary interface between energy seller and buyer in its region through the planning resource auction. And how we accomplish that interface planning interface role is really through a combination of macro and micro lens when we're planning for resource adequacy and reliability. Again, over and over again, we have talked about the changing landscape, the changing paradigm. How is it changing the balance of the generation and also load? What it also comes with is a layer of uncertainty. And as we start thinking about preparing for the real-time dispatch and balancing the generation and load, it also leads to a conversation about, do we have enough bandwidth? Do we have enough system that is planned ahead of time that we get into the operating zone? And so the purpose of the macro view, which is the outer layer of the constituent circle, is just to visualize how the region's generation fleet could evolve over a longer time horizon. So we're talking about 10 to 20 years out. And this is done just based on members' resource planning activities. And so it will foreshadow the evolving operating conditions as we had previously visited, as well how the risk is shifting. So the objective for this planning, this different kind of horizon planning is really just to shrink the size of uncertainty as we move from planning horizon to operations. So how this can help you? The insight can help MISO states and members to really connect the plans and goals to system impact. And so we will include how we need to plan for our transmission system, how our market may need to evolve, and how operations and reliability may ultimately be affected. And so the next couple slides, I will walk through the varying planning studies and resource adequacy methods. And so I will begin with the macro study, which is the outer circle, to focus on planning, and then moving into more immediate micro lens, which is the very center of that bottom circle. That's a more near-term time horizon. Okay, so the outer layer of our process is regional resource assessment. And this assessment really uses a public shared plans and goals of the region. And what we try to do with that information is to develop a forward-looking view of evolving resource mix across the MISO region. So we collect data from our members based on generation addition, retirement, as well as a load forecast. Historical carbon emission is a part of that data collection, and as well as a plan or goals to reduce carbon emission and or to increase their use of renewable energy. And so this collection of information is intended to provide utility state regulatory agencies and MISO with a better insight into expected resource changes over the coming years. And so this in turn would assist our stakeholders with the critical information that's needed to plan for grid of the future and ensure the continuing flow of reliable, low-cost electricity. And so this is where we have a lot of insights generated from the regional resource assessment. And so we can test different kind of theories, some of them, some of which Todd had shared, different concept. And then we share sort of a continued capacity risk, highlighting not just the immediate importance of additional investment, but also awareness to what the surrounding members or surrounding neighbors are doing in a regional perspective. It's not included in this presentation, but I also just want to give a quick highlight to even a higher level, at a macro level of a planning study, which is our Renewable Integration Impact Assessment, or RIA study. That's just to assess what broad trends are anticipated and looking at those inflection points where we have to make a decision on the risk profile, or if our construct, adequacy construct is sufficient. So those are at a very high level, macro level. We're looking at the just trends and how the system condition have changed. I do also want to share very quickly a snapshot on one of the outputs, which you may find interesting. And so this is an aggregated view based on the survey. So what you can see is typically when we are designing our resource expansion plan, we lack that visibility across and to look at the regional and the system view. So the study is designed to really see at collectively what are some of the continued capacity risks we may see, and again, what are some areas that we need to invest in putting a little bit more focus on. So I think we can talk about the slide in detail, but I do have a little bit more material to go through, so we can certainly circle back. And this is a very interesting slide, so I do want to come back to it if the time permits. So now we have the insight from the outer layer of the macro planning. And so we want to talk about how we're going to use this information, or how we're going to use that information and start shrinking the level of uncertainties. And so what we would do is, if we have positioned ourselves at the outer layer to relay the insights we gained with our states, with our members, and hopefully that would lead into a better, a more curated resource expansion plan. And so this is what we would implement in our transmission planning process. So what you're seeing here is a set of process called MISO futures, MISO planning futures. And so what we're doing is translating utility and state goals into critical planning scenarios. And this is to just looking at what are the bookends of future uncertainties. And we use long-term planning analysis, require the applications of a sufficient resource throughout the study period. We're also looking at amount of resource needed typically exceed what's currently known or public planned by members. So there are confidential information that we will collect in this process. So in MISO's futures process really help to fill the resource gap and showcase the area of focus throughout MISO. Next process is our OMS, which stands for Organization of MISO States, and MISO survey. And this survey is conducted annually. It's purely voluntary, although I have to say the participation is very high. So it's in the upper 90s. And the purpose for this survey is to assess available resource capacity to serve projected load over the next 5 years. So as you can see, each step of this process, we're bringing that insight, we're bringing the conversation a little bit closer to the operating horizon. So this is going from 20 years from regional resource assessment to now we're talking about 5 years. And so this was the only study of its kind when implemented. And you really give MISO and members in our footprint the first visibility into the regional trends. So load serving entities and utilities within each zone, we have 10 zones, must have just sufficient resource to meet load and required reserves. And any kind of surplus resources may be shared among the utilities or load serving entities with a deficit to meet the reserve requirement through our resource capacity auction. And the survey really evolved over time to improve its accuracy. As we kind of mentioned when we first kicked off the survey process, it was one of its first kind. And so we understand there's going to be a maturity curve we apply to this process. So as we start seeing surplus resources tighten, more accurate counting of expected available capacity is paramount. So in collaboration with OMS, MISO made changes to ensure that resources anticipated to be available and reflected in the MISO OMS survey are accurate based on the trend and likelihood of being available in the year projected. This is very consistent to the regional resource assessment report. We're seeing a similar trend here. And so, which is that available capacity is decreasing in the near term with expected retirements and new resource taking time to come online. So there's a little bit gap in the subtraction and the addition of a generation. We understand, so we talked about the first couple of layers of the macro planning lens. And so understanding each of the three long-term outlooks, while they're aligned, they are designed to meet different purposes and functions. And so what we have done here is to summarize and comparing the three different processes in terms of purpose, description, scope, and linkage for you to take a deeper look. And we're continuously evaluating what long-term outlook are used for. And so how do we use it, information? How do our audience use the information? And so we can better improve the forward-looking process. Okay. Next, we're going to transition and moving towards the MISO resource adequacy process that prepare our members for the operating horizon. And so that one way of doing that is the annual planning resource auction, or known as PRA. So this process is demonstrating sufficient resources and allow market participant to sell capacity via the auction to other market participants who may be expecting a shortfall. So it's really creating that information gathering process to have a transparent augmentation. In recognizing the system has varying profile for each season, as we start talking about with renewable penetration, its performance through ebbs and flows of season, as well as a load changing. So we recognize that there's a different type of needs for each season. So we conduct and issue a resource assessment in advance of each season that evaluate potential resource adequacy risks. So this is, again, just another layer of information to provide insight. This is an informal assessment that evaluate projected near-term available capacity under some extreme peak load forecast and historical outages. And this is mainly for generation outages for each season. And these assessments highlights potential issues in the upcoming seasons to help the system operators and the stakeholder preparing for the potential strained system condition and develop preventative actions. And I'm really glad the question of resilience came up a few times. So I think this is where we can also have a lot of conversation is through the seasonal assessment. This is just another snapshot about how we shrink the size of uncertainty and really bring in the ready, aim, and execute approach. And so how do we account for extreme weather? And based on the statistical data from a little further out, a seasonal look, and then gradually, as we have available information and more refined information leading into just real-time conditions hours ahead, there's different types of process that we account for this availability of this information to manage uncertainty and risks. Then lastly, this is where we're really trying to bring everything out together, and how we practice resource adequacy is really through how we balancing the generation load in real time. And so here is a different kind of metrics and reports for us to understand, did we get it right? Did we do all the planning correctly? Did we pre-position the system correctly? So as we have more extreme weather, increasing in emergency warnings, alerts, and events, and more attention is given to real-time operations, forecasts, and data. And so this is becoming really a data issue for all of us. And so this is where we also want to add another insights to regulators and also to media. And this is our published information, just an example of that. And so it looks like real-time condition, but also post data to look into the real-time operating condition, really understanding what's driving the different type of pricing, the different type of commitment decisions as well, and ultimately testing our process, how we actually carried out the planning all the way to execution in real time in terms of resource adequacy. So in summary, the fleet changes has already occurred. This is evident from several different conversations, and we know this is still more to come. So when we think about how we look at risk, market design, and tool development, it's again paramount to understanding how these tools process metrics that was designed for a different type of a past scenario that may or may not exist for the direction we're moving towards. So capacity plan to cover a single peak hour. This is something that we already seen. Todd said the best is from a capacity standpoint, we really need to also looking at energy-based adequacy planning as well. And so those are some of the plans we have moving for present and future, is really just looking at the supply margin, fleet changes, and also adding the consideration of extreme weather. And so from those scenarios, we formulate really what are the right metrics for us to look at to ensure adequacy in all hours of years. We're redefining markets to facilitate this outcome. So last year, FERC approved our proposal to shift from an annual resource adequacy construct to a distinct seasonal requirement and accreditation to better account for the seasonal variation that we kind of mentioned previously. And this is just a first step. I think knowing the complexity that's coming our way, we had additional initiatives underway and elevated to the priority that the organization is focusing on, so we can ensure system needs moving forward. We are also improving coordination with our neighbors. And so a lot of the conversation is, we know all the infrastructure, we know all the additional generation will slowly trickle in, but to meet the immediate focus when we have more of a retirements than generation coming online. So what are some of the stopgap measures? So leveraging neighbors' import and export capability is definitely one of those. And we will continue to evaluate our scarcity pricing mechanism to again provide the right price incentives for the market to respond. And then there is also continuing effort in gas electric harmonization effort, recognizing the importance of that coordination in the next few years. So with that, we have all the planned materials. So Todd and Elliot, I'm going to turn it back to you to see if there's additional conversation or questions that populated.
Hey, thanks so much. That was terrific. Great to hear what's going on in MISO. And there weren't any questions in the chat. I'll put one your way, and that's just sort of thinking about the state regulators' perspective. You mentioned the organization of MISO states, obviously, as a forum to engage with MISO at the state level. Are there other efforts in MISO to kind of understand and capture the regional impacts of individual state energy policies that might have an impact on the resource mix at a more local level? And I don't know if you can speak to that.
Absolutely. I think there's a couple of efforts that we can get involved in. And so when we started the regional resource assessment study, it's really to provide that regional view. And it's based on the 10 zones that we have inside of MISO. And this is where we received a lot of feedback from regulators, from our members, to say how important it is that granular view provides visibility to how things are changing. The other benefit of regional resource assessment is it's being done at an annual basis. So you can track and you can also see how the system is evolving and how incrementally these measures that we're putting forward is effective. So there's definitely that regional resource assessment. I encourage everyone to participate. On the other side, there is also a paired conversation about reliability attributes. And so MISO, in the past few months, I have held discussions. It's a extension of what we talked about here in terms of resource adequacy, but looking at reliability attributes, what are some of the key attributes that we need to keep in mind in designing some of the construct as well as evaluating performance? And so we have identified 3 areas. Number 1 is flexibility. So this is regarding to real time. How are we meeting the ramp requirement? How is the ramp requirement behavior is actually changing with the penetration of renewable? And the second area is planning adequacy. So again, looking at some of the different constructs we have explored. Direct LL is one of them, and there's a different type of accreditation that methods going into that. And so it's all start to understanding how does generation of the different kind of portfolios penetration's impact on the accreditation for each of the type of resources. I believe Todd kind of mentioned this as well, is we start seeing a portfolio bias. The more of the same resource we add, we actually lower its accreditation. So that's a primary focus for the planning accuracy, is looking at what different type of balance or augmentation or mixture of a resource portfolio will need. And lastly, which I think we don't talk enough, which is the impact of inverter-based resources and its impact on system stability. It's really, there's a lot of great things that these different kind of technology can help actually thinking about how our system needs. And so that's the attributes conversation. And we are going to merge these different regional resource conversation assessments in the view with attributes. So it provides more layers into what specific risk are we looking at. We know the risk is shifting, capacity is not enough, we need to look at energy, but we also segment into that 3 specific areas to understand the impact and also thresholds as we navigate the transition. So Elliot, I don't know if that was too much or too little for your question.
That was terrific. I really appreciate it. And again, appreciate your expertise and your presentation on that. And thank you so much. We're going to keep things moving now on schedule and go to our final presenter. I'm going to hear from Nick Pappas. Nick Pappas is an energy industry consultant focused on policy and market design for the electric sector. Nick leads a boutique consulting firm focused on supporting the energy transition, with particular emphasis on the intersection of reliability and decarbonization in the utility resource planning. Prior to establishing his consulting firm, Nick held leadership roles in regulatory and legislative policy at the California Community Choice Association, Southern California Edison, and the California State Assembly. Nick holds an MS in Energy Systems and a BA in Economics from the University of California, Davis. Nick, thanks for doing this. I guess if you can share your screen and get your slides up, I'll turn it to you.
Awesome. Thanks so much, Elliot. Let me get my screen share going, and thanks for that intro. I should have sent you a shorter bio. That was a mouthful. But maybe just a little introduction in the context of this group for this discussion. So I mostly work in Western markets, and Elliot invited me today to talk about how RA is transitioning across Western markets, across the WEC. And perhaps in contrast to some of the earlier presentations, a lot of the discussion in my presentation is going to be about the sort of application of RA, taking it out of the model and into the sort of policy and compliance world. So let me just go ahead and screen share. I've got more content than we're going to get through in 25 minutes. A couple of big topics tried to embed here that each of which could be an hour or two talk. So I want to just really encourage folks to jump in the Q&A if you have areas where you would like to ask a question or to go a little bit deeper, or try to get a little more context. Please don't hesitate there. So just want to confirm, can folks see my screen share, see the presentation?
Looks good.
Awesome. Great. Thanks, Elliot. All right. So RA in the West. So RA is a pretty complicated topic in the West. A lot is changing. In today's talk, I'm going to go briefly through sort of why RA is changing in the West, talk a little bit about the physical transitions occurring as well as the policy transitions, and then share a couple of regional updates. So one from the Western Resource Adequacy Program, which is an emerging multi-jurisdictional RA program. You can see its members on this map in green. And then the West's other big RA program, which is that overseen by CAISO and the California Public Utilities Commission, which is the only ISO region in the WEC, at least for now. And then talk a little bit about some of the future trends. So again, a lot of content here, more than we're going to get through in 20 minutes. So please don't hesitate to raise your hand if you want to kind of dig in more depth on some of these topics. So this deck is a bit of an aggregation of a few talks that I've given around each of these individual issues. So to kick it off, I pulled up an old slide deck. This is probably 3 years old now, about why RA is changing in California. And I want to set the stage in California because I think that's going to be very informative to what's happening more broadly. So beginning around 2020, at the time that California had its first load shed in 20 years during a summer heat wave, we saw the initiation of a bunch of really big RA reform initiatives. Around the same time, regulators across the West and utilities across the West were developing their Western Resource Adequacy Program. It was really driven by a few key trends. So one is the resource transition, going from conventional firm resources to this new suite of diverse use limited resources. I think folks heard a lot about that this morning. Going from regulated utility portfolios to a diverse competitive market. So California has recently been going through a sort of vertical utility deregulation process with the formation of community choice aggregators. It's maybe not a perfect parallel to other regions, but probably some similar dynamics happening elsewhere. We went from a sort of robust ability to rely on neighbors to a new market dynamic where demand and outages across the region became increasingly correlated. So we see that in California with extreme heat increasingly impacting the whole region as opposed to sort of one of the segments of WEC. And then we have, of course, forced outages from thermal sort of occurring around the same time during those heat waves. You might see a similar parallel in other markets, thinking about cold snaps and impacts to fuel supply. Climate is reducing our confidence on hydroelectric resources. We have new drought risk emerging. And then finally, and I think this trend is pretty cross-cutting geographically, just going from a market that was long for many years to a market that is now very immediately tight, whether we're talking about energy, capacity, etc. So anyway, I dug this out of an old slide deck, and I wanted to give it an update to talk about the West. And fortunately, all I had to do was cross out California and write in the West, because all of these dynamics are driving the same kind of RA reform in the West that we're seeing in California. And this is a NARIC audience, so I thought maybe there's other folks from the US or Canada or elsewhere who are here. So I wanted to make it more generalized. So I went even further and decided to make it general. And so again, I just had to cross out California and the West and write in everywhere, because I think these themes are really quite cross-cutting across regions. The main change here when we look at everywhere, again, is sort of looking at climate risks beyond demand and hydro in the West, and looking at the, in particular in Eastern markets, the very severe implications from fuel supply risk on the natural gas system and how that interacts with electric generation outages. All right, so jumping in on some of the detail on what those reform initiatives look like. So just to set the stage, RA in the West looks very different from RA in the East. So in Eastern markets, well, excepting the Southeast, RA is really dominated by capacity markets within ISO regions. So most of these are, buy all, sell all capacity markets in the East. We have a sort of residual market in MISO. And then SPP and CAISO have bilateral RA markets, which are somewhat unique, but share a lot of similar dynamics to the other ISO capacity markets. Until now, and perhaps until later in the 2020s, most of the West lives in an RA world that is not part of a formal regional system. RA has essentially lived inside of each individual utility's long-term planning exercise. Typically, that's governed by a state utility commission, and it's largely existed in silos. And that's raised a lot of concerns for a number of reasons, but in particular driven by the interactivity of each utility's IRP with resources controlled or held by neighboring utilities. So you might be a utility that is short, but you've always been able to count on the Pacific Northwest having excess hydro that you could buy in the market. You didn't have to think too much about resource adequacy, and it was just a sort of simple assumption in your IRP that you could rely on some of that import capacity. When 2020 hit and the market tightness arrived in full, I think that assumption was really shaken, and that has really driven, I think, a lot of the impetus to move forward with RAP and try to get a formal structure to increase that kind of coordination. So we'll talk more about RAP later, but just to set the stage, RAP is going to, when it launches in the late 2020s or sort of becomes binding in the late 2020s, it's going to cover the majority of WEC load. It's here on the west of SPP, essentially, that is not currently covered by CAISO. So about 2/3 of non-WEC load will be covered. And I don't know if folks can see my cursor. This area in green essentially represents most of urban WEC, with the exception of Colorado. A lot of the white space that we're seeing here is co-ops, rural areas, which, for reasons that are beyond explanation by me, opted not to join RAP. Perhaps they will moving forward. So just a little bit of context. I don't think these issues need too much introduction, but essentially the evolving reliability dynamics, we've got the same kind of dynamics that are happening throughout the country. Resource retirements, particularly a lot of coal is retiring. We saw a lot of gas retire in the 2010s. We lost a nuclear plant in 2012. So just a big shift downward in the supply stack. A lot of emerging clean resources. Folks heard a lot about ELCC and saturation effects this morning, but essentially trying to sort of appropriately account for those resources reliability contributions. Climate and load growth are also just shifting a lot of the other fundamentals. So both how severe the severe weather is and how frequent the severe weather is. And load growth, we've got, both electrification and also, just like other regions, huge expected load growth from data centers. This is a graphic from WEC, just looking at planned additions and retirements in WEC over the next 10 years. And you can see we have a pretty big shift in the resource mix, with a lot of firm thermal resources retiring and a lot of clean energy resources expected to come online. I'm going to breeze through a couple of these slides, but just want to emphasize, some of the trends that we're seeing from a resource planning perspective. We're seeing shifting hours of risk, and I think that was discussed at length in some of the presentations this morning, but just to visualize this is the CAISO net load. So net load is essentially CAISO's gross load, so it's total demand minus clean energy, so intermittent solar and wind resources. And this is the sort of infamous duck curve updated to this year. And you can see that in each year, the net load belly of the duck is getting deeper and the neck is getting steeper. So what does that mean from a resource adequacy perspective? This is happening sort of in stages, but we start, and this was a lot of the discussion in the 2010s, was we need resources that can ramp quickly. So for a time, that was largely gas resources. Increasingly, folks are looking at storage, being able to provide that ramping service. We see a shift in the net peak. So this graphic, starting in 2015, we can't see what the old gross load was around 2010, but essentially we've seen a big shift from mid-afternoon peaks to a net peak that's now 6 to 10 p.m. and moving even later with each year. And then we are, now we're trying to solve the net peak with storage. And there's a tremendous amount of storage being built in California, being built across the WEC. What we see is the width, the duration of time that storage needs to fulfill is lengthening with each passing year. So the widening net peak is reducing the effectiveness of that storage capacity, which is a critical element to plan for using ELCC or other tools in our modeling framework. And then finally, and I think this is really emerging as a theme, is we can make a ton of progress with solar and storage, particularly if we augment this with wind, but we really have to start looking at what do we do outside of those peak solar periods? What are the clean energy resources that we're looking at that are going to fill in this long, 12 to 18-hour gap, depending on the season, when the sun is not shining, that is going to be supported by battery storage, but clearly is going to take a much broader set of resources than simply 4-hour storage. So I'm going to just take a couple minutes on what's happening with the Western Resource Adequacy Program and California's RA reform, and then I want to pivot to questions. And Elliot, please jump in if anything comes in the Q&A. I don't think I can see that pop up. So a couple of regional updates. I'm going to talk through some updates from the Western Resource Adequacy Program. These are largely drawn from a report that I co-authored with Grid Lab, which is available here, and the links will be in the deck when it's circulated. Talking about how RAP should be viewed from the perspective of state regulators and utility planners trying to pursue long-term planning through their IRPs with this new requirement that exists in RAP. So RAP is, first off, I'll just say, a really impressive step forward and represents, quite impressive coordination from utilities across the West coming together and essentially assembling a voluntary compliance program outside of an ISO construct. I don't think anything like this has happened before, and it doesn't have a lot of parallels in terms of the level of coordination, except perhaps, some of the ISO formations happening in the 2000s. And RAP is, essentially going to become a near-term RA program. So RAP has a sort of 5-year planning horizon and a 1 to 2-year compliance horizon, and it creates a clear framework for utilities to have a sense of what their RA responsibility is in the context of the region, with clear accounting rules, a clear PRM, and clear compliance and non-compliance costs for them to consider in their resource planning. What RAP is not is a replacement for long-term planning. Because of its short planning horizon and sort of limited midterm assessments, there's only so much that RAP can do to solve RA, and we have to figure out and how does RAP sort of complement rather than replace utility level planning. So here's a map of the RAP participants. It's the majority of large utilities in the West, about 2/3 of non-CAISO load in the WEC. Just to visualize what this looks like. So RAP looks pretty similar in concept to the CAISO bilateral program, perhaps the SPP program as well. I'm not as familiar with that, but essentially similar to the CAISO program in that there's a summer and a winter showing, but the summer showing, like CAISO, is monthly, and it's based on resource counting values for each month. So you can see an illustrative showing on the right-hand side where a utility would stack up its resource portfolio. The value here is expressed in ELCC for solar, storage, and wind resources, and then other counting methods for other resources. And then in the bottom left here, you can see the planning horizon. And I think this is in focus for RAP as a new program, but I think this kind of intersection and challenge between the RA program and the planning horizon is really present in RA programs and capacity markets throughout the country. I think it's certainly present in MISO and in other Eastern markets, in CAISO, where we have a formal RA program, but that RA program is not inherently doing the long-term reliability planning for these member utilities and member states. And that's a tension we've seen come up in a lot of these discussions about sort of the purpose and application of these capacity markets. So this, just to tee up, one of the major challenges I see with RAP. RAP uses ELCC. Don't get me wrong, I'm a supporter of ELCC, but ELCC is very difficult to implement in practice when you are one member of a complex planning region with lots of different decision makers. So if you're using ELCC in the context of an IRP, your model can look at your planned clean energy investments and say, okay, here's where I'm going to be on the ELCC curve in the future. If you are, one member of a 20 utility RA program, that ELCC saturation curve and where you are on that ELCC saturation curve depends on what all of the other utilities in that region, as well as merchant generators and others, do to develop resources. And this is not just a complexity and sophistication problem. Certainly you need sophisticated folks at the utility and at the regulator to kind of understand the concepts here. But even the most sophisticated folks have limited ability to meaningfully predict where we're going to be on that clean energy development curve. If there's one thread that has tied together clean energy development across regions, is we have one expectation for the pace of development, and then historically that has largely been smashed with much more aggressive deployment. In the last couple of years, that trend has reversed with some of the supply chain challenges and interconnection challenges. But again, it just emphasizes the unpredictability of how these saturation curves will play out in real time. So if you're a utility, it's 2027 and you're planning your position in 2030 or 2035, how do you think about how much your resources will be valued in the context of that program? All right, I think just briefly on this, I think RAP, again, is a huge step forward. It creates, it solves a huge collective action problem, provides utilities a lot of information that, largely has been sort of rough estimates and IRPs, particularly around import assumptions and market resource availability. It has some other benefits around reducing, operating reserves and facilitating sharing during contingency events. But it's not a panacea. It doesn't obviate the need for the utility and the regulator to really meaningfully engage with long-term resource needs and planning outside of the construct of RAP. And our paper goes into more detail on the key areas there, but predictability is a huge one. And I think just also the medium and long-term horizon challenge is really significant here. Let's jump into California. So California, one of the more complex policy landscapes. I think folks would generally view California as having an RA black box in the model, and then also having sort of a policy black box that we're all trying to figure out as it constantly evolves. We have three major changes in resource adequacy coming in California, in addition to the dimension of just physical changes that we're managing and modeling changes. We have three massive policy changes. The first, it's probably gotten most coverage to date, is the transition from an ELCC-based RA program to a slice of day RA program. I'm going to talk through that on the next few slides here. We have an impending proposal within the integrated resource plan proceeding that will establish multi-year reliability and emissions compliance standards. Remains to be seen whether that's going to be based in ELCC or slice of day. And then we've just had a legislation passed and signed by the governor that establishes a central procurement entity, which I think is largely viewed to be there to do the sort of hard procurement that individual LSCs, particularly small LSCs, can't commit to. So things like offshore wind that might have a 5 to 7 year lead time, perhaps large-scale geothermal development, long-duration storage, things like that. So moving from ELCC to slice of day, so this graphic here on the left-hand side shows, hypothetically what a resource showing in the RA program looks like today for a single month. On the right-hand side, this is what it'll look like under slice of day accounting. And so the general context of this transition is that California's LSCs and regulators, and there's something like 40 LSCs that the commission regulates, we're really struggling with ELCC on a year-to-year basis. ELCC changed regularly, it was unpredictable, and this is by design. ELCC is designed to adjust as different effects from the portfolio occur as the portfolio mix changes. So it's a feature, it's not a bug, but it made it really difficult when an ELCC refresh occurred and it fundamentally reshaped the value of solar, storage, and wind in a way that was not predictable by LSCs. And I should say we never actually implemented ELCC for storage, but the need to implement ELCC for storage and the challenges with that represented a big rationale for the commission to move to slice of day. So slice of day essentially unfolds the monthly showing into 24 hours of a representative day for each month, with representative resource profiles for solar and wind, and then sort of a direct application of storage and demand response based on its capabilities. And the intent here was to give LSCs and also give regulators a little bit more ability to directly manage how those interactive effects worked in the portfolio. I should say it's also a function of the view from regulators that it was critical for each LSC to be pulling its own weight in terms of bringing sufficient energy for storage charging, et cetera, not sort of leaning across the system. Just quickly to sort of take you through how this works from an LSE perspective. So this is the system portfolio in the mid-2020s with lots of solar and storage. As an LSE, you essentially get your resource requirement, which is your load forecast plus a PRM. You show your firm resources as 24-hour blocks, and then you fill in whatever else you need with solar, storage, and wind. You're obligated, if you show storage, you're obligated to show excess energy from your energy producing resources to be able to charge that storage, including some round trip losses. And then that storage, even if it's a 4-hour resource, it's dispatched based on its capacity megawatt limitations and its energy megawatt hour limitations, as opposed to a sort of flat downgrade. So if you have 6 or 8 hour storage, you can show that in the same manner, utilizing its full resource stack or full attributes. Let's see. I think one of the key themes that came out of the transition to slice of day was helping LSE planners and regulators see that we are likely to continue to need 24-hour resources for a very long time. This is true in the summertime, but it's especially true in the wintertime. And I think this is really the intent of slice of day, is to give LSEs sort of a tool to do that analysis and homework as they're thinking about their mid and long-term integrated resource plan investment decisions. I'm going to skip over this as we wrap up here. Just one common question a lot of folks ask, does slice of day obligate your storage resource to be dispatched in the way that it's modeled here? And just a clarification that I think has been useful in some of these discussions is slice of day is really just about how it's shown to the regulator. Your resource still gets handed off to CAISO to dispatch economically consistent with RA resource obligations for market participation. So just a couple thoughts on the long-term trajectory for WEC. We've got big shifts in the market fundamentals, just resource transitions. Long-term planning, we have a lot of efforts from utilities and regulators to sort of evolve their tools, whether it's the actual tools themselves, inputs and assumptions, et cetera, as well as the policy frameworks to try to be prepared for this sort of next and more complex round of RA in the 2020s and 2030s. And then regional collaboration, I think no West-wide conversation would be complete without mentioning the ongoing efforts to develop an ISO in the West. We have a lot of activity right now, sort of a struggle between CAISO and SPP and other players for who's going to sort of ultimately run that ISO market. So let me maybe wrap it up there and see if there's any questions. Elliot or others, if not, I'm happy to keep talking for 2 minutes, but not seeing anything in the chat or the Q&A.
Yeah, nothing in the chat. Again, encourage all participants, if they have anything they want to ask Nick or the other presenters, please go ahead and drop that in the chat or the Q&A at this point. Nick, I guess I'll quickly kick it off. I'm wondering about the wrap, and you spoke a little bit about the mechanics of it and the sort of the runway into when it becomes, I guess you could say, mandatory. Could you speak a little bit about the background and a little bit more on the West? And maybe I know there's the energy imbalance market, and they have some requirements for the entities that participate in that in terms of they have to carry their share of I think it's like flexible, you can't lean on your neighbors basically. But this was more complex and more difficult to come to fruition. I'm wondering if you could speak to why and what are the barriers? Because I think in other parts of the country, regional sort of coordination is going to only become more important as you have different states with different policy goals and different resource mixes with political boundaries, basically.
Yeah, Elliot, it's a great question. There's probably a couple dimensions to answer this on. So this initiative, I think, became increasingly of interest in the mid-2010s as utilities were seeing those resources they'd relied on neighbors for start to sort of shrivel up in the market. And maybe two dynamics that sort of separate the West from other regions. I mentioned that most of the West is not part of an ISO, so there hasn't been this sort of formal structure for RA sharing or coordination or transmission planning. And then sort of in parallel with that, the West has a lot of interregional exchange. So you think of our Northwest hydro assets and sort of Southwest fossil assets, increasingly sort of Southwest solar assets as well, have been sharing a ton historically. And I think you saw Southwestern utilities, California utilities, start to see those, essentially the native loads in the Northwest rely more on the hydro resources, the ability to count on those hydro resources for everybody declining. And folks were starting to sort of see the writing on the wall that the net resource balance was shifting into the red. And I think whether you're, there are a lot of utilities with lots of different sort of market and philosophical positions on this, but just as one hypothetical, envision yourself as a Southwest utility. You'd like to continue to rely on those Northwestern imports, but you don't really have a framework to do that. Imagine yourself as a Northwest utility. Maybe you have some excess hydro. You'd like to sell that, but there's not really a framework to do that. I think there were benefits on all sides to do this coordination, but you can imagine how difficult those conversations are to say, let's agree on a dollar value for penalties for non-compliance as a group. That's a really difficult conversation, particularly when you have entities with different market positions who have different incentives there. And so lots and lots of different kind of challenges to resolve through that process. So it's quite impressive, I think, to see this move forward in the way that it has. But I think we all kind of rely on each other, and this was an outgrowth of the need to formalize and recognize what had long been those bilateral or informal transactions. So you asked about EIM. So EIM is the energy imbalance market, really designed for sort of momentary transactional interregional trades managed by the CAISO. Super beneficial in terms of sort of managing those moment-to-moment changes. And it does have some requirements. Everybody has to show up in the day ahead with sort of a sufficient level of resources. I'm going to get the details wrong. I'm not an expert on this, but the discussions around the broader EIM and sort of broader markets would probably extend the planning horizon. So the sort of extensions would, like, if we were to form an ISO, it would take you from these, sort of very short-term assessments to like a year ahead, multi-year ahead planning horizon. And at each extension of that planning horizon, you get more and more benefits. So like EDAM, the day ahead market, lots of discussions going on now of how that should kind of move forward and who will be participating. Like EDAM, so day ahead relative to the imbalance market, brings much more value in terms of economic dispatch in the day ahead market for resources across the West than just doing it moment to moment. And you could extend that a year ahead or even 5-year ahead planning allows a lot more of those sort of economies of scale and economic trading opportunities to occur.
That's very helpful. We've got about 9 minutes left. I'd love to pull in Dr. Levin and Dr. Elizondo. I'll see if I can spotlight both of you, and maybe we just do some sort of cross-cutting questions here to wrap up. So this is sort of up for grabs for all of you. I guess, we didn't talk as much about the role of transmission, but maybe you could speak a little bit to that. I know this is a tough one because there's a lot, a lot going on in terms of interregional and sort of these longer lines and the needs throughout the country. But in terms of sort of transmission as a resource, if you're if you're thinking about our audience here and commissions, to what degree do you think the role of transmission or transmission will play going forward in this transition? That's a very open question.
I mean, maybe I'll start. I mean, I would just say, obviously, well, maybe it's not obvious, but I think it's very important. And maybe kind of from the perspective of my presentation, at least, and others as well, is that the key thing is that the transmission system, transmission capacity will impact these resource adequacy metrics. And so, it's the difference between, let's say, a traditional planning reserve margin and something more ELCC based or other, another evolving metric, what's more system oriented. And that I think that's a recognition, at least, of the fact that, you can have reliability, resource adequacy issues that come up because of transmission constraints, and that wasn't necessarily, as usually traditionally considered, kind of independently in the past.
I'll just share, I think there's a couple ways I see this in the planning framework. So there's one question of transmission, which is maybe existing resources today that can't get to load, and that's a missed opportunity. And that can help, two regions both reduce their RA requirements if they have, complementary diverse resources or diverse load. So I think that's huge, and that's definitely in focus, particularly in the West, as we think about, broader transmission planning. And RAP might help identify some of those issues, but it's not a transmission planning entity. There's different initiatives there. I think as we look 5 to 10 years out, perhaps an even bigger transmission opportunity is the limitations of the existing transmission system to facilitate individual utilities from accessing diverse clean energy resources in other areas that are super complementary. So rather than like 3 times as much solar in your state, you have 1 time that amount of solar plus some complementary wind plus some complementary geothermal. And there's elements of that are physical and I think live in the modeling space, but there's also a lot of elements there that are contractual, and particularly in these non-ISO regions, how do we flatten what is today a lot of friction between regions in the transmission space?
Mm-hmm. Yeah. So, and I can add something on in line what was commented is. It's also very important to consider that the transmissions in the models and tools that we use to evaluate the resource adequacy or capacity expansion or production cost model, so that those are considered in there, and you know, to assess the ability of the certain areas to bring resources from other areas when they are in trouble, no? And we can think of several examples of events that happened before, like, you know, the events in Texas, that, you know, that after the fact we think that perhaps they could have used more transmission, or perhaps in California a couple of years ago when there were shortages in the summer, that should we also look at transmission in there. So I think it's very, very important, and perhaps consider transmission at all of the modeling steps that we use in planning. Yeah.
Terrific. Got a couple questions in the chat here. Any insights on how or if we need to think of resource adequacy differently in the context of a region like ISO New England that is expecting to shift from summer peaking to winter peaking? For instance, the duration of scarcity events could be days, not hours, depending on cold weather conditions.
I can jump in here. I think this is a really central question in Eastern markets right now. So first, I'll just say the identification of that winter risk is a huge step forward, and we're seeing that happening in ISO New England, in PJM and MISO, a little bit less in New York ISO, but just the general Eastern market intersection with cold snaps, thermal outages from cold, fuel supply issues from cold is huge. Where I have some concern with some of the implementation today is in an ELCC construct, it's all built around probability distributions. And so if we try to aggregate the whole year, we have very low confidence in our prediction of how frequent and how severe cold snaps will be, their impacts on the gas system, et cetera. And so trying to kind of balance one ELCC for a whole year that sort of splits that distribution between how likely we're going to have a summer event versus how likely we're going to have a winter event, I think is really problematic. So regions that are looking at seasonal approaches that sort of distinctly identify the summer risk and the winter risk, I think are going to be a lot more successful here than pretending we have enough confidence in the distributions to do it all together. And I can't recall offhand if ISO New England is doing seasonal. I think they're exploring that, but I can't recall offhand.
I'll just kind of pick up, I think what I talked about too, and there was a question after my presentation on the, you know, revisiting capacity credits essentially for thermal resources. And I think, you know, the ELCC or other metrics come out of the system model, and they're based on whatever the inputs you put in to the model. So if you assume uncorrelated outages with, you know, like Nick is saying, you have to assume probabilities, and, you know, some of those low probability events are hard to assess. But if you're able to use more sophisticated models that actually simulate, you know, weather conditions or weather dependent outages that might be correlated across, you know, common modes and things like that, then you will start to get better metrics. But again, any kind of modeling is, you know, it's the garbage in, garbage out philosophy, but, you know, it's dependent on understanding or knowing what those probabilities are, and that's not always easy or possible. So it might be one other thought, you know, it might be a slightly separate framework too. You have sort of a more standard operating condition resource adequacy assessment, but you do sort of a, you know, extreme operating condition assessment on top of that, and kind of maybe use a slightly different approach and supplement it.
Yeah, definitely. Yeah, just to echo Todd's comment, I think it's and also from my point of view of detail-oriented engineer, it's yeah, I think I would also do perhaps complement the resource adequacy analysis with more detail models, and also depending on the event, you know, like if the events are like lasting a few days or a week, then it's one tool that you may use. If it is a sudden outage, then you may use, you know, a different tool. So yeah. So I would say have a suite of tools, and depending on the region and the type of events that are expected on those regions. Yeah.
Yeah, it seems hard to imagine not looking at duration more carefully going forward of these events, and in general with energy assessments, things like that. But I guess we'll close it out here. We've got one more question that might be kind of fun to rapid fire. Will we ever achieve a carbon-free grid? So I guess we could just go around short answers if you can.
maybe go first. So I think, yes. The question is when, and by yes, I mean it could be 200 years from now, right? It could be 15 years from now. But I think it is, kind of the slightly more nuanced answer is I think it's certainly possible. It's more in kind of current climate. It's more a question of political will and economic will than technical challenge. I'm not saying it's not a technical challenge, and the power system engineers get mad at me when I say this, but I know it's challenging, but I do think it is, largely possible with technologies we have today. It's just, do we want to get it done, and do we want to pay for the difference between 90% and 100%?
I largely agree with Todd. I think I'll say I feel pretty good about the first maybe 60 to 80%. I'm feeling pretty excited about some new technologies. Geothermal in particular, I think, has kind of a moment coming up here. And maybe a kind of optimistic, pessimistic comment. I'm more optimistic about reaching a fully decarbonized grid than any other industrial sector. So stay hopeful there.
Marcelo, anything to add?
Oh, sorry, I was muted. Yeah. Yes, I also agree. I would say yes as a short answer, and it will take a lot of effort from us, from from the industry, from research, community. And I think we can do it. We have to work hard and take the challenge. I believe, and the questions, as Todd was mentioning, the questions on when that's. We will see. I think, but I think it's a very good, very exciting time, and very good work for us in front of us. Yeah.
Well, again, really appreciate all our speakers today, and thank you all for sticking around. And we'll see. For those who want to attend Thursday, we'll see you at the same time, same place. You got the link. So please join us Thursday, and then again next Tuesday on generator interconnection. Thanks again, and we'll see you Thursday. Bye.
Thanks.
Thank you.